Now, going to the wind load. All these four parameters that I mentioned, which is time period, displacement, and frequency and acceleration, all of these are typically controlled by the wind loading in a tall building. Now, there are certain reasons why this happens. So that is why I chose to use wind loading for this presentation. Now, to understand in simple terms, there's a wind. If you see the image on the right, there is a wind acting on a building. Of course, building becomes an obstacle to the wind path. So the wind has to go around the building. So when you say it goes around the building, it goes along the direction of the wind itself. And also there is a component which goes in the perpendicular direction. So there are two components the wind is converted into. One is along wind and the other is transverse wind or crosswind. Now this is wind from one direction, shown for illustration purpose only. Understand the wind could happen from any direction around the building. Now throughout the presentation, we'll be talking about one direction to just convey the concept of how we are designing this. Now the characteristics of wind itself. Why is wind so critical to the tall building design? The first characteristic is your wind velocity increases with height. So the wind force you face at 50 meters above ground is much lesser the wind force that you will face at 300 meters above ground. So for a short building, your wind load may not be governing the design, but when you have a 300 meter or 600 meter tall building, your wind force is too high, and then that governs your overall design. So that is the first factor. The second is wind turbulence. Again, as you go higher above the ground, the flow of the wind becomes turbulent, which creates eddy currents, etc., into the building. So one of such phenomenon that is created is called vortex shedding phenomenon. I'll explain briefly about vortex shedding phenomenon because this is one of the critical characteristics of wind, which is considered in the design of tall buildings. And there are many buildings which are designed around to avoid this phenomenon from occurring in their building. The last one is wake buffeting. In short terms, we can say if you're walking between two tall buildings in any location, you will always feel the wind force is higher in this location than a place where there are no tall buildings. So the wind, when there are two tall structures, there's a lot of wind pressure occurring between these buildings itself. So that is a phenomenon again called as wake buffeting. It just means you're channeling the wind forces into a certain location, which creates more pressure on the buildings. Now, like I said, the most interesting, at least for me, in terms of wind characteristic is the vortex shedding, because many of the tall buildings, if you care to read about the design of various tall buildings around the world, you will come over again and again the term vortex shedding. So this is one of the major phenomenon that is considered in the design of tall buildings. Now, what is vortex shedding? Is basically you have a wind. I can go to the next slide. So this is an animation of how a wind flows around a building. Now, this circular white thing that you see at the center, just consider it's a building. It's just supposed to be circular for some reason. But anyway, this can be any shape, but just consider this is your building. Now, there's a wind flowing from one direction. It hits the building, so it has to change its path. So it goes around the building. It goes around the building. Now, like you see here, after a certain height, your wind force is so high that it doesn't have a straight path after the building location. The wind flow becomes turbulent here. It becomes turbulent on both sides. So what this one does is it creates low pressure regions across these two flow patterns. So there is varying low pressures which happens across these two flow patterns, which puts a certain force on your building, and thus your building is subjected to also move along these two directions. So that is when you have a crosswind response in the building. So you can see the same thing in your image below. So there's a wind flowing, there is vortices developed, which creates a perpendicular force on your building. Now, this perpendicular force is what is called as the crosswind response to a building. And generally, more than the along wind response, it is this crosswind response which creates a lot of challenges in tall building design. So that is why vortex shedding is generally considered to be a critical parameter in the design of tall buildings. Like I mentioned here, at low speeds, there is no tendency for this to happen. So for a short building, this is not supposed to happen, or this generally doesn't happen because your wind forces are much lower. But at tall building, the wind forces are higher, which means your building is going to be subjected to vortex shedding here. I'll go to it slowly. So how do we decide what are the wind loads acting on a structure? Now, you all know that we have codes in ISO, in Indian standards also, we have codes defining what are the wind loads to be acting on a structure based on the geographical area, based on the buildings or the surface around it, based on the wind speed in that area, etc. Now, these codes have certain limitations. These wind loads cannot be used above a certain height of the building. So as per, again, an American standard here, the wind loads determined from the code are expected to envelop most building structural shapes. Buildings or other structures that are clearly unusual should be designed using wind tunnels. So that is where wind tunnel technology is used. Now, a tall building is definitely an unusual shape. Generally, wind tunnels are recommended in the following cases. So whenever there is a building which is greater than 200 meters, which is a tall building in itself, it is recommended to go for a wind tunnel testing to understand what is the load acting on the structure in terms of the wind within that location. There are also other parameters, but as a designer, generally the height of the building is considered to be the most critical parameter. So whenever there is a building above 200 meters, we recommend the client to do a wind tunnel testing. Now, what is a wind tunnel testing? This is one of the interesting aspects of a tall building design. Now, wind tunnel testing is a procedure where they make a model of your building. In this picture, if you see, this is the prototype of Shanghai Tower, I think, from China. So they prepare a scaled model of the building to be tested, which is in a different color here. And they also model all the buildings around it. Now, the reason for modeling all the buildings around it is, like I said, buffeting is one of the phenomenon. For example, there's a tall tower here, there's a tall tower here. The force within these two towers will be much higher than the force on the other side because there is no obstruction there. So that is the reason they go about modeling the buildings around it to a certain diameter, to a certain distance around it. Now, once the model is done, they put it in a tunnel. That's why the name wind tunnel comes, and they subject to certain wind forces. How they create the wind forces is through jet fans. So they set the jet fans to certain speed of wind, which is based on what is the wind forces expected in that particular location. So this is what they generally do, and this is what I've explained here as well. So they generally test this building for the force that it is expected to act, and they see what is the response of the building. Now they test for two conditions generally. One is the existing condition. For example, this may be the existing condition where there is already buildings around it. There is also a future condition. For example, there is another tall tower coming here. They will do a separate test with that tall tower as well, because you may design a building at this current time based on whatever is around it, but the wind loads will change definitely if there is a taller building coming later. Of course, we cannot predict what is going to happen after a certain point of time, but if there is knowledge that there will be a tall building coming in recent times, they will also do a wind tunnel test for that condition. So that are the two conditions they will do the test for, and whatever wind loads they calculate will come out from both of these, the maximum of. Now, I mentioned that they do an analysis of this tower based on whatever wind load is acting. Now, it is not only about the wind forces acting, it is also how they study the response of this building to the forces. So in order to do that, they need certain parameters from the structural engineer to model the building and also to understand its response. So that is where there is a role, or there's a discussion between a structural engineer and a wind engineer to decide what is the response of this building going to be, and what are the loads that are acting. Now, I just put in the steps that we generally follow in the design of a building in a design office itself. So first step is the structural engineer builds a 3D dimensional analytical model to obtain the geometrical behavior of the building. So this is where your softwares like ETABS or MIDAS or Robo Analysis, there are many softwares. You can choose any software to create a three-dimensional analytical model of your tower. You build the model, you apply the loads on it, and you study the behavior of the building. Once you have the behavior, which is basically the structural data, I will explain in the next slide what are the data that we share to them. So once we obtain the structural data from the analytical model, we will share these with the wind tunnel specialist. After this, the wind tunnel specialist will build a scaled model, like I showed in the previous slide, including the surroundings, and then simulate the wind loads based on the climatic data available, which is from your weather monitoring stations, etc. You'll get this data. And then they study what is the impact of this force on the building. So once these tests are done, these results are shared back to the engineers, which is in terms of your displacement, your frequency, your acceleration, etc. And they also give you the loads that needs to be used in the analysis. So once we get these loads back, we again include these loads in the analysis model, and we try to check if all the members are passing, if the deflection is within the limits, etc. Now, if the deflection is within the limit, if all the member sizes are working, everybody is happy, we finish the project and we go home. But this generally doesn't happen. So whenever we get a load which is different from what we have initially assumed at step one, we will have to again go back to the wind tunnel engineer, and we have to tell them that no, we need to change something, that we get a displacement which works. So there is two things here. Either we change the lateral stiffness of the building, like I explained before, to control the displacement, or they propose some changes in the overall dimension or overall geometry of the building, which will also help in reducing the wind load. The wind tunnel specialist, so there is an iterative process here. It could be 1 time, 2 times, some projects it goes till 10 times, trying to find out which is the best shape for this project, or which is the best height that can be achieved for this tower in this area within all the economical aspects. So the wind tunnel specialist also gives a feedback on the human comfort criteria. Like I told, he says what is the acceleration expected in this building, and we can check if that acceleration is within the allowed criteria, which means any humans at a certain height will not feel any sort of discomfort. He also gives you what is the pedestrian comfort. For example, you have a balcony in a tall building at 200 meters height. There's going to be a lot of wind pressure coming there. So the wind tunnel specialist will tell you, yes, you can put a balcony, or no, you cannot have any balconies in this building. So that is another criteria that they study. And now this is generally what happens between a structural engineer and a wind engineer. Like I told you, there is some structural data that the structural engineer passes on to the wind tunnel specialist. This is basically listed here. One is the ETABS typical floor plan showing the location of the origin, which is your center point of the building. Then you have these two-story heights, which is your floor-to-floor heights across the height of the building. You have a structural damping, which is basically the type of material you are using in your design, and certain parameters which come directly out of ETABS. I'm not going into detail of all these because this is a bit more advanced in terms of understanding and away from the scope of this presentation now. There is also some architectural plans and 3D modeling that is shared. So the wind tunnel specialist can build his own prototype model for testing. Now, once what we get back from the wind tunnel specialist are the wind forces and moments. As structural engineers, we are only interested in forces and moments. We don't care about anything else mostly. So they give us what is the forces to be used on the building. They give us what is the combinations to be used. Like I told you, the wind acts from all directions. So they tell us at a given point, which direction is critical and how we combine these different directions. So that is a list of combinations they give. They also give you results for different damping values, then existing and future conditions, like I told you. And then they give you the acceleration values and pedestrian comfort criteria, which I just explained in the last slide. Now, like I said, in order to mitigate the displacement, one way of doing it is to increase the lateral stiffness of the building. The other way is to provide additional dampers. Now, this is only a very brief idea. So in general, what they do as damper is they put a heavy weight on top of your building. So it basically provides additional stiffness and controls the displacement. This is an example of a damper which is located in Taipei 101 building, one of the tallest towers in the world. And this is also a tourist attraction. People are allowed to go and see this. This is, you can search it on Google. It's very impressive in itself. So in terms of design process, there are generally 3 stages that we do in design office. One is the concept design stage, which is basically finalization of built-up area, column wall arrangement, building geometry, number of floors, MEP requirements, etc. So this is generally done by the senior technical people within the company, which is the directors or team leaders or principal engineers. The second stage is the scheme design stage, where we finalize all the structural element sizes. This also includes all the wind tunnel communication that we do with the wind tunnel engineers, all the iterations, and then finally we come up with the structural element sizes. And we coordinate with other disciplines like mechanical, electrical, and facade, etc. So this is generally carried out by senior structural engineers, lead project engineers, with a team of engineers, of course, to assist them, and BIM modelers. BIM is your Revit model, etc. The final stage is detailed design stage, where it is preparation of your reinforcement details and closing out any coordination issues, and basically you prepare drawings for your construction stage. This again is done by a similar team with led by structural engineers. So when in terms of a career path, when you join a company, you'll probably start being in this team of engineers trying to help a senior structural engineer. Maybe you will design a column here, a beam there, or a slab here, and you will be part of a big project. But as you grow in your career, as you gain experience, you'll move here to your senior structural engineer or a lead project engineer, and there will be a team of engineers working under you. So this happens maybe with 8 to 12 years of experience, or 8 to 15 years of experience. So you need to have a lot of patience to really move up the ladder in structural engineering. And with further experience, maybe 15 plus years of experience, you will be part of a team leader or a director who decides on the major issues in the building, such as the building height, etc. So that will be your career path. You'll be growing from the bottom of the table right up there. And you need a lot of patience also. So coming into the job opportunities, as a structural design engineer, I work predominantly in the building sector, so I can quickly check what are the opportunities in the building sector. So obviously you need a structural design engineer, you need a geotechnical engineer who defines the foundation systems and the soil properties of the foundation, etc. Then you have BIM modelers. Now there is a trend in India where there are a lot of engineers going into a BIM modeling to design into Revit, etc. And there's definitely a huge future there as well. The whole construction sector across the world is moving into 3-dimensional drawing, and also trying to get everything into a 3-dimensional model, which helps in coordination, etc. So that is also a very impressive field for the near future, at least. Then you have the quantity and estimation engineers. You cannot build a project without knowing what you're building. So definitely you need quantity and estimation as well. Next one is planning engineers. Planning engineers generally decide the duration of a project and how the project is phased from design to construction and to handover. Then you have design coordinators who coordinate between different disciplines such as structures, MEP, or facade, or architecture, etc. Then obviously you have site engineers to execute the work on site. And there are temporary works and erection engineers. So temporary works is all the scaffolding you need to build a building, or you need, if it's a steel structure, there is a certain erection sequence that you need. So this in itself is also a major field for engineering. So these are some of the opportunities that you will see within the building sector itself. Now, as civil engineers, this is just one portion of what you can achieve as a job opportunities. There are various other sectors, various other job opportunities as well. Now, in terms of career path, I just wanted to share some views because I understand most of the participants will be graduates or early engineers here. So I thought I will just explain what a senior engineer will be expecting from a graduate. Now, firstly, any senior or any experienced person know that a graduate is a graduate. So they will not be expecting too much from you, but there are certain basic requirements that's expected. So one of them is graduation is only start of the learning curve. So once you finish your master's or your bachelor's, it doesn't mean that you have finished studying civil engineering. It is only the basics of civil engineering that you have studied. So you should always be open to learning more. You need to keep learning across your career, because if you stop learning, there are a lot of chances that you are not going to grow further. So in order to grow in a career, you definitely need to learn, and it is an attitude that you need to develop, that you are ready to learn as much as you can. So that is one attitude that people in the interview will be seeing if you're ready to learn and you're ready to progress yourself. Second one is, a part of learning is be curious and persistent. Try to find the information that you think you want to know, and be curious to ask questions, but again, ask questions in a professional way, and learn how to ask questions to whoever it is within your field. So that is what I mean by learn to network with professionals working in the same field. You have a lot of options now like LinkedIn, etc., where you can connect with people and try to learn things if not available within your same office or any place where you work. Next one is, you, like I said, learning is a continuous process. So you need to enhance yourself with additional skills, which can be softwares, your licenses. When I mean licenses, it's license from the local authorities, like a registered engineer, etc. You need accreditations, internships, certifications, etc. So all of these will help you to increase your skills and also maintain a continuous professional development record. If you don't know what it is, you can always Google and check. It is basically a track of what you are doing to enhance your skills. And if you're, when you attend an interview, if you show that you have a continuous professional development, which just means that you are showing the interest to develop yourself in the career, and it is a positive impact that it makes on any person who's interviewing you. And finally, I just say own your work, which means take responsibility for whatever work you're doing. So even if you're asked to design a single beam in a tall building, just make sure you do it with all your focus on it, and just make you basically take responsibility for your work, which is very critical as well. And at the end of it, I also would like to mention that you need to learn a lot of softwares now, because everything is software, but do not follow any software. A software is only as good as the engineer itself. So if the engineer is good, he knows how to use the software, and then you get the required result out of it. Just knowing a software doesn't mean you know engineering. It works the other way. You need to be a good engineer to use a good software. But there are a lot of softwares now, a lot of ways to get licenses, accreditations, etc.